Hello, I'm Sheldon Axler, the author of Linear Algebra Done Right. This video discusses the section of the book titled Rn and Cn. You should be familiar with the properties of R, the set of real numbers. Even if we were interested in doing linear algebra just with real numbers, we would be forced to consider complex numbers. The reason for this is that the real numbers are not rich enough to have zeros for non-constant polynomials. For example, the equation x squared plus 1 equals 0 has no real solutions. Thus, we invent a solution, which we call I. We can actually make this rigorous. Here's how to do that. A complex number is formally an ordered pair a comma b, where a and b are real numbers, but we will write this in the much more suggestive notation of a plus bi. The number a is called the real part of a plus bi, and the number b is called the imaginary part of a plus bi. The set of all complex numbers is denoted by c. Addition of complex numbers is defined in the obvious way. We just add the real parts and add the imaginary parts separately. The definition of the product of two complex numbers is less obvious. You can see the formula here. There is no need to memorize this formula. Just use the distributive property and expand the product in the usual way by replacing I times I with -1. We can think of a real number a as the same as the complex number a plus 0i. Thus, we think of the real numbers as a subset of the complex numbers. We also usually write 0 plus bi as just bi. Finally, we usually write 0 plus 1i as just I, completing a rigorous definition of I. Note that the definition of multiplication given above, with a and c equaling 0 and b and d equaling 1, shows that I squared equals -1. Addition and multiplication of complex numbers have the usual properties that you expect from arithmetic. Here is a quick list of those properties. Addition and multiplication of complex numbers is commutative, meaning that order does not matter. Addition and multiplication of complex numbers is associative, meaning that grouping does not matter. Thus, in expressions such as alpha plus beta plus gamma, or alpha times beta times gamma, we do not need to bother with parentheses. 0 is the additive identity for addition of complex numbers, and 1 is the additive identity for multiplication of complex numbers. Every complex number alpha has an additive inverse, which we denote by -alpha. Every complex number alpha, except 0, has a multiplicative inverse, which we denote by 1 over alpha. The usual distributive property holds for multiplying the sum of two complex numbers by a complex number. So that we can conveniently make definitions and proof theorems that apply to both real and complex numbers, we adopt the following notation. F denotes either R or C. Elements of F are sometimes called scalars, which is just a fancy word for numbers. The letter F is chosen to represent either R or C because R and C are examples of what are called fields. In these videos and in the book, we do not deal with fields other than R and C. However, if you know what a field is and you want to think of F as a more general field, then you can do so for many of the results in the early part of this course. As motivation for defining Rn and Cn, which appear in the title of this section, we first consider two familiar special cases. Let's begin with the set R2, which is the set of all ordered pairs of real numbers. As you know, we can think of R2 as a plane. Next, consider R3, which is the set of all ordered triples of real numbers. As you know, we can think of R3 as ordinary space. The idea of thinking of a plane as the set of ordered pairs of real numbers was popularized by René Descartes in a book that he published in 1637. This painting shows Descartes explaining his results to Queen Christina of Sweden. To generalize R2 and R3 to Rn and Cn, we first need to discuss the concept of lists. For now, we will consider only lists of numbers, but later we will need to consider lists consisting of other elements. Fix a positive integer n. A list of length n is an ordered collection of n numbers separated by commas and surrounded by parentheses. For example, 7, 3 is a list of real numbers. This list has length 2. Thus 7, 3 is an element of R2, which is defined to equal the set of lists of real numbers of length 2. As another example, 5, 9, negative 2 is a list of real numbers. This list has length 3. Thus 5, 9, negative 2 is an element of R3, which is defined to equal the set of lists of real numbers of length 3. A list of length n looks like this, where each xj is a real or complex number. Two lists are equal if and only if they have the same length and the same elements in the same order. Now we define Fn to be the set of all lists of length n of elements of f. If f equals r and n equals 2 or 3, then this agrees with our previous definition of R2 and R3. But our definition of Fn makes sense for larger values of n. For example, R4 is a set of all lists of 4 real numbers. As another example, C4 is a set of all lists of 4 complex numbers. Note that in the notation for C4, we use the symbols Z1, Z2, Z3, and Z4 instead of a different letter for each coordinate. Realistic models of the economy can have dozens, hundreds, or even thousands of variables. Thus, using a different letter for each coordinate quickly becomes impractical. The notation of one variable with a subscript to indicate the coordinate works well. We have geometric models of R2 and R3 as a plane or as our usual space. It does not matter whether R4 and R400 or C4 and C400 exist in some real geometric sense. These sets have elements that consist of lists of 4 or 400 numbers, and we can manipulate them algebraically as easy as we can manipulate elements of R2 and R3. This is why our subject is called linear algebra. Elements of Fn are often called points or vectors. This geometric language may help lead you to think about analogies to the geometry of R2 or R3, but you do not need to worry about whether or not R400 has a physical realization. An element of R400 is simply an ordered list of real numbers of length 400. We define the sum of two elements of Fn by adding the corresponding coordinates, as shown here. For example, here is the sum of two elements of R4. Scalar multiplication, which means the product of a number and a vector in Fn, is defined by multiplying each coordinate of the vector by the number. For example, here we have the vector I, 2, 5 plus I, negative 3i, which is an element of C4, and we are multiplying it by I. The first coordinate of the product equals negative 1, because I times I equals negative 1. We have seen that a typical element of Fn is the list x1, xn. However, it's often more efficient and cleaner to use a single letter to denote an element of Fn. For example, here is a clean statement that addition is commutative on Fn. Here x and y each denote a list of n numbers, but there is no need to write them explicitly as x1, xn, and y1, yn. The symbol 0 gets used in multiple ways in linear algebra. For example, 0 can denote the element of Fn consisting of a list of n zeros. This means that the symbol 0 is ambiguous, but it should always be possible to tell which meaning is intended from the context. For example, consider the following result, which states that if x is an Fn, then 0 times x equals 0. The 0 on the left, which is now in red, must be the number 0, because we have not defined the product of two vectors. The 0 on the right, which is now in red, must be the vector 0, because the product of a number and a vector is a vector. Remember that the word vector simply means an element of Fn. This concludes the video on Rn and Cn.